In this video, we'll start looking at DC circuits, and in particular, we're going to start looking at how to combine resistors that are in parallel and series. This follows very much the same line as what we did for capacitors in parallel and series. You can put resistors in parallel or in series to make larger or smaller resistors than you could purchase, for instance, from the company. So, if you place them in series, it's effectively the same thing as making the length here longer. And we remember that the resistance was equal to the resistivity times the length over the area. So if you make the length longer, then you're going to make the resistance go up. So you put them in series if you want to make a larger resistor. Now we can figure out what that's going to have to be. If this is plus minus V1 and plus minus V2, and we're going to make this go from point A to point B for a given amount of current, because they're in series, we're saying that for the same thing, we're making a single resistor, REQ, and we're putting a total voltage for the same amount of current. So, what is that going to do to us? Well, what that does is we find that V has to equal V1 plus V2, but this is equal to I times REQ. V1 is equal to IR1. V2 is IR2. So if we divide out the R's, the I, we get REQ is equal to R1 plus R2 plus how many of our resistors. So resistors in series look like capacitors in parallel. And all we did was use the fact that the current going through each one of them is the same I everywhere, no subscripts, and that the sum of the voltages is equal to the total voltage across the equivalent resistor. So that's the idea behind the proof. This is I, that has to be I. You'll want to put that formula to memory. It's a very useful formula. Now if you make them in parallel, this creates a smaller resistor. And if you look at it, you can see that's like you made the area bigger. The other way to think about it is, look, you had a pipe and you were flowing some water through this pipe. If you had a second pipe added to it like this, you could carry more water for the same push. That makes the resistance effectively go down. Remember, the voltage is like the push or pressure, and you're looking at the amount of water, which is like I, and the resistance. So if you can make a bigger I for the same push, that means this R went down. That went up, that had to go down. Now, you can prove the formula for here by realizing you have the same voltage across all of the elements in parallel. So all of them have the same V, but they have different currents. So this is I3, this is current I2, and this is current I1. But all of it had to initially come in here to conserve charge. So that's the amount of current here, but you'll have the same voltage in this case since it's in parallel. So let's see, the voltage here is equal to, or I should say the current here, I, is equal to V over REQ. And that's equal to I1 plus I2, but plus I3 and whatever else. But this is equal to V over R1, V over R2, V over R3. We can cancel out the voltage since it's the same for parallel and we get the formula 1 over the resistance of the equivalent resistor is equal to the sum of 1 over the resistances of each of the individual resistors. So resistors in parallel look like capacitors in series. Let's do some numerical examples on this after we cover a couple of shortcuts. Remember, there were some shortcuts for capacitors in series? Well, there'll be equivalent shortcuts for resistors in parallel. If you have two resistors in parallel, and it only works for two, then it's the product of the resistors divided by the sum. This is exactly the same formula we had for capacitors in series. And if you have identical resistors in parallel, it's simply the resistance of one of them divided by the number that are in parallel. This is the resistor divider rule. Exactly the same formula that we had back for a bunch of capacitors of the same capacitance in series. These two shortcuts can really save you some time on a test like the AP exam or UIL. Here's an example problem. What is the resistance between terminals A and D in the following circuit? Like with the capacitor, we need to figure out which ones are in series and which are in parallel. And I usually like to start as far away from where I want to find the original final equivalent resistor, which is between A and D. So I'm going to start out here. These two resistors are parallel because their voltage across them is VBC. And here, VBC. Because all points here are the same point. And all points here are the same point. So these resistors are in parallel. So we can combine those two resistors, and because they happen to be in parallel, we have the nice thing, and they're the same value, that it's 4, and I have two of them, so it's 4 divided by 2. So we can reduce our circuit now to a 2 ohm resistor, 2K ohm, a 2K ohm resistor. This is at point A, this is at point D, connected to point B and point C, and between that, a 2K ohm resistor. This was 4K ohm over 2, which gives us 2K ohm. But now we have three resistors in series, so we simply sum up their resistance. So REQ is 2K ohm plus 2K ohm plus 2K ohm is 6 kiloohms. And that's the equivalent resistance of this circuit. Let's do another example. What is the resistance for these two? Now here's an example where I have two resistors in parallel. So REQ is R1, R2 over R1 plus R2. I have 6K ohm times 4K ohms over 6K ohms plus 4K ohms. Well, 6 times 4 is 24, divided by 6 plus 4 is 10. 24 over 10 is 2.4. I would find it harder to add 1/6 plus 1/4, add that together, and then take the inverse. If you have a calculator, yeah, you can do it, but a lot of times you need to be able to do these type of things quickly in your head, and this product system works, but it only works if you only have two of them. If you have more, you have to take them two at a time. Here's another circuit, three of them in parallel, but they're all the same, so REQ would be equal to R over 3. 9K ohms divided by 3 is a 3K ohm circuit. So with these rules, it is possible to very quickly find the resistance of any type of circuit in which you just have a series of resistors that are in series and or parallel. More complicated circuits we'll get to later are going to require more complicated rules, but these form the basis of some of those, so you need to master these. Okay, we'll see you in another video.